Okay, starting out, we're still in 1.3, still rates of change, but we are focusing in on linear and quadratic functions specifically, okay? Over any length, input value intervals, so those are my x values, right? The average rate of change for a linear function is a constant, okay? Or it is constant. It will be a number only, okay? Technically, it has a, you know, like rise over run, that just same thing over and over and over again. But for a linear function, right? But the constant, that's where we graphed this line up here yesterday, okay, where it will just give me a flat line, okay? Technically, a constant, which is a number, has a variable. It's just x to the 0 power, because anything to the 0 power is, 1. So that multiplied by the number is fine, okay? And it just gives you that number. All right? Now, given consecutive equal length input value intervals, the average rate of a quadratic function can be given by a linear function. Linear functions are x to the first power. Those are y equals mx plus b. So we know quadratics are x squared. We know linear functions are x to the first. What do you notice about the average rate of change, the function that would represent it? Its power is 1 degree less here, okay? Thank you, Parker. Okay, it's 1 degree less here. All right, the average rate of change over the closed interval a to b. This is what we've been doing, okay? A to b, x to x. The slope, this is the slope of what we call our secant line. It's the slope of our secant line. Okay? Now when we talk about concavity again, okay? Average rate of change and concavity. In a quadratic function, that's our parabolas, okay? We can determine curvature or concavity of the graph by considering the average rate of change over equal length x intervals. Sketch our secant lines on the graphs shown below, okay? Now, right here, I'm recording. All right, it says sketch secant lines on the graphs below. Now, we've already done this once this semester, okay? Now, my secant lines, they're going to look like this. Now, right here, my function is decreasing on this part of the parabola, okay? But then it gets to that minimum, and I have a rate of change of 0, okay? And then it starts turning, and I get positive slopes. So it makes a turn, and then it starts increasing. So for any concave up function, the further I go to the right, it is increasing. For a concave down function, okay, right here, it's increasing. Then I get right here to the maximum, and the rate of change is 0. And then it changes direction, okay? It's going up, but then it turns, and then overall that slope is decreasing. Okay. All right, flip it over. Let's look at example number 4. Okay, it says using the function from example 2, we've already got the picture right here, okay? We're going to use that same function, which is f of x equals x squared minus 6x plus 5, all right? let's consider what the graph of the average rate of change for this quadratic function will look like. All right, what did we just say for quadratic functions the secant line will look like? For a quadratic function, the secant line, or the average rate of change, is going to be a what kind of function? Linear. Yeah, it goes down 1 degree. All right? Now, this parabola was concave up because my leading coefficient was positive. My leading coefficient right here was positive. Also, because the average rate of change on the equal length intervals is, and we'll get to this, 2. I'm sorry. I need to say increasing and then 2. By a factor of 2. I'm sorry about that. It's increasing by a factor of 2. Now it says, let's call this the slope of my new function, okay? Now, down here it asks me to graph my new function, so I'm going to go ahead and I'm going to say m equals 2. Now, we also observed yesterday on example 2 that the quadratic function changes from decreasing to increasing at the vertex, and that happened where x was 3. Now, what did we specifically claim the rate is at that vertex? 0. Yep. Okay. We say that the slope is constant. Sorry. Okay, and then it says you can use the ordered pair as my x value and then the rate of change. Okay, so x and rate for a point on the graph. So a point on the graph that I'm going to have here, I'm going to rewrite this because I want y'all to know this is where it came from. The place where the turning point happened, where the 0 rate of change happened, was at 3. Okay, right here, 3, 0 is a point on that graph. And if my slope was 2, you can go up 2 over 1 as many points as you can, okay? But you can also go down 2, back 1, down 2, back 1, and you can see, nope, sorry. I need to use that ordered pair to help me find what my y-intercept is going to be. Ignore what I just did right there. I'm just plotting that point 3, 0. Okay? So, knowing y equals mx plus b, and I know that this point is on the line, I'm plugging in 0 for y, I'm plugging in 2 for my slope, and 3 for my x value. Do what? Oh, I don't have any. You can go get some. You bleeding? Okay. It's okay. All right, so I'm going to solve for b. This is 0 equals 6 plus b. So if I were trying to get b all by itself, if I subtract 6, I'm going to get that my b value is negative 6. So my equation here is y equals 2x minus 6. Rise 2, run 1. Rise 2, run 1. Rise 2, run 1. Okay, and that gives me enough that I can plot my point. Sorry, that's not perfectly plotted or straight. It is hard to see those grids on this particular copy. Okay, and this right here is my secant line for that function. Okay? All right. Example number 5. Okay, it says, let's generalize the procedure for finding the average rate of change or velocity to any function over any interval. Okay, right here, I'm given the function f of x is x squared plus 2. And I want to find the average rate of change from my time t to time t equals 2 to time t equals 4. What am I going to do with 2 and 4? Yep, I'm going to plug it in. F of 2 and f of 4. Thank you.
Oh, these are the x values.
Those are my x values, yes. Okay? Hey, just FYI, I already have phones up here to turn in. Don't let yours be anywhere near you. Okay? Right here, I've got 2 squared plus 2. Okay? 2 squared plus 2. So that's going to be 4 plus 2, which is 6. And then when I plug in 4 to that function, 4 squared is 16, and 16 plus 2 is 18. So my 2 ordered pairs that I'm finding the slope between those points are 2, 6 and 4, 18. I'm going to have 18 minus 6, and then I'll have 4 minus 2. 18 minus 6 is 12. 4 minus 2 is 2. So my average rate of change on this interval is 6.
Okay, so nothing's really changing from what we were doing before. It's
Nope.
just continuing.
Yep. I know Career Academy is getting here late, but if y'all get here late or y'all come in late, it is your responsibility to get the notes from the videos. Okay, I will help you in tutoring after you get those notes. Okay, and I need the whispering to stop. All right, now for part B, I have the exact same function. Okay, but I'm asked to find the average rate of change on the interval 2 to 2 plus h. Okay, so right here, I already know 2. That's 2, 6. I just calculated that one. That was the 6th time that my door's been knocked on in this class period. Don't ask me to go anywhere. Right here, okay? I know that my output is already 2, 6, okay? Now, when I have an algebraic expression and I plug an algebraic expression in, what am I going to get out? Another algebraic expression, okay? So right here, I'm going to plug in f of 2 plus h. So I am literally dropping in the algebraic expression 2 plus h into my equation. Okay? Please do not just distribute that exponent of 2. That exponent tells you how many times you have to list this as a factor. You have to do polynomial multiplication. So this is where you use the distributive property. I'm going to do 2 times 2 and 2 times h. So that gives me 4 plus 2h. Okay, and then I'm going to distribute the h to both of these. So that's another 2h and an h squared. But then in the back, I still have that plus 2 that was part of the original function. Okay? I've got 4 and 2 that I'm going to put together. So let's see. I'm going to say 2 plus h has the output 6 plus You got 4h plus h squared.
You're not gonna do h squared and then 4h instead?
You can put it in standard form, but I'll fix that in a little bit. Okay? Now, when I calculate my average rate of change, I'm asking to generalize what's happening. Please remember, when I'm finding the slope, or finding the average rate of change, you're finding the slope. So right here, I am finding f of 2 plus h minus f of 2 over the difference of the inputs. Fortunately for me, I know what these are. They might be algebraic expressions, they might be numbers, okay? F of 2 plus h is this whole thing right here. So I'm going to go substitute. Okay, you can go ahead and swap it around if you want to. I don't care. Plus 6, and then my slope here. Let's see. I'm going to go ahead and put the 2 plus h in the bottom. And then f of 2 was 6. All right, now I see some like terms. Okay, I see some like terms. Okay, you got the 6 and 6, and the 2 and the 2. So this simplifies right here to h squared plus 4h over h. So right here, if you left your answer in this format, yes, that is equivalent, but it is, you would get maybe 8 out of 10 points for all this work right here. The reason is because you always must simplify your fractions. And there is a GCF that happens right here that you can take out an h, and the h's cancel. So this simplifies to h plus 4 as your final answer for your average rate of change.
So we don't take like the h in the...
Well, I mean, I took it out of both of these terms, but I took it out to the front. What are you saying to take the h out of the parentheses? So like right here you're talking about?
We keep that one.
Yes.
We don't take
Well, the h is coming out of both of those. This is h squared plus 4h. So when I took it out of each one, it just removed the h and put it out front.
Okay, so this is how you want that to be done when we have a...
Yeah. This right here is simplified.
You said we don't do this, that's only 8.
Well, if I'm just saying, for example, like if this part was worth 10 points and you gave me this, yes, that is equivalent, but it's just not simplified. So you'd only get like 8 out of 10 points. Okay? Okay. Next, right here, I want to write a general formula for the average rate of change, the difference quotient for any 2 points. Okay? I've got 2 points right here. I've got a f of a, and I have a plus h, f of a plus h. So I am going to show my average rate of change. I do change in y. So I'm going to do what I would like to consider as the more difficult one first, minus f of a. And then I'm going to do the inputs right below those.
You're saying it's more difficult because there's 2.
Because you got more stuff in there. Yep. Do what? A plus h. Oh, well, hold on. So right here, there is nothing I can do to the top. Okay? You would have to have the actual algebraic expression to be able to simplify that. Okay? But you can simplify the bottom because both of them have the a, and it's a minus a. So all I'm left with in the denominator here is that h. Okay? Yes, that's simplified. You can't do anything with this because you don't know what the output is. Okay. Now, let's take a trip to something easier for a second. Okay? All right. When you're trying to determine whether a given table represents a linear or quadratic function, we want to check the differences. Okay? All right. What do we know about linear functions? They should constantly increase at the same thing. All right. Right here. How do I get from 4 to 1? Subtract 3. How do I get from 1 to negative 2? Negative 2 to negative 5? Yep. So you're subtracting 3 for every single one of those. Okay? This happened the very first time that I found the differences. So therefore, this is called the first difference. Okay? Okay? Now, if the first difference is equal, then it is a linear function. It represents a linear function. Yeah, if all of these numbers, if you're finding the differences, okay, and it's like by increasing by the same thing over and over again, okay, the first time you do it, if it's the first time, that's going to give you a linear function. Now, take a look at the next one. What am I doing to get from 12 to 0? Subtracting 12. What am I doing to get to 0 from 0 to negative 4? Yeah, so I already see that that's not the same, right? Okay. Negative 4 to 0, I'm going up 4. And then I'm going up 12. Those aren't equal. So I want to go to the next difference. What do I do to get from negative 12 to 4? Negative 4. Add 8. What do I do to get from negative 4 to positive 4? And I add 8 again here. So this one right here, the differences were equal the second time. So this is what I call a second difference. Okay? And if it's a second difference, then it represents a quadratic function. What do you think it would be if I had to go through and find the fourth difference? Nope. If this is x to the first power, x to the second power, the fourth difference is not going to be quadratic. The fourth difference is, y'all, cubic is the third. What's the fourth power?
Oh, wait, did you say, wait.
Yeah, I heard you, Earl. Quartic. Did you say that? Oh, I thought you did. Was that Janaris? Is that you? Oh, good for you.
Good job, Ash.
Okay. So x to the third power would be a cubic, so that would be the third difference. Okay? Yeah, I mean, it could be some random thing. Or it could be an exponential function or some different kind of function family. Okay? Yeah, it's possible. Okay, here we go. Let's take a look at example number 7. Okay, example number 7. Right here, given this function, and I've got the picture shown at the right, find the average rate of change from -1 to 3. I'm going to work smarter, not harder. I'm going to go find my points on my graph. So when x is -1, my output was -4. And when my x value is 3, my y value is +4. Okay? Now, I want to find the average rate of change, so all I'm doing is finding the slope between those 2 points. So I'm going to do 4 minus -4. And that means I have to do 3 minus -1. So that is 8 over 4, which is 2.
Oh, we could have just counted it as well, too,
Yeah.
right?
Yeah, but it was asking me, yes. Okay, now, right here it says, write the equation of a secant line containing those points. Now, real quick, if I use my slope to help me graph more points. Hey, can I ask you this before you come in here? Can you run back to the front office and grab the DoorDash delivery that was sent? There should be 4 lunches. Thank you, baby. I love you. Okay. All right. Rise 2, run 1. Hey, there's my y-intercept. Rise 2, run 1. Rise 2, run 1. And then rise 2, run 1. There, it connected those. Okay. So this is my secant line. And its equation is, if I put it in y equals mx plus b, that's y equals 2x minus 2. And then I just graph the secant line because it hit at -2.
Oh.
Okay? Why are you looking at me like that? What's your question?
Do you do that with the point?
Do I do it with what?
Like, if there was no graph, can we do it with the point?
Yeah, absolutely.
Alright.
Okay? All right, question. Do you have any questions for me? So far, it's just being very tedious, right? Finding the slope over and over and over again, okay? All right, while you are in here, before lunch and when you return from lunch, you have until then to complete your 1.2 practice, and it is mine at the end of class, okay?
Guess I got.
What?
Brother needs some assistance.
I'm going with an A.
I had an 82.
Okay.
But that's way